Okay. Hello, everyone, and a very good morning to you all. My name is Sushil Mane, and I welcome you all to the second webinar for this 3-series session that we had. The first one was yesterday, and that was on Compose and how you can use Compose for doing CAE post-processing. Today we'll be having the second one, which is basically a course simulation of different simulations that you would want to do with 0D, 1D, and 3D. And the topics will be basically covering Activate as well as MotionSolve. The presenters for today are basically Gitesh Porwal, who is the technical manager for multi-body dynamic simulations, as well as Chandra Kumar, who is the senior application engineer. Okay, so over to Chandra Kumar, and then he will start the presentation.
So very good morning, all. So today's webinar outline will be introduction to Activate, introduction to MotionSolve, and then course simulation between MotionSolve and Activate, and its application and case study, and then we'll have Q&A session. So before, hello, am I audible? So can you hear me? You can put a message in the chat window. Yeah. So before going into presentation, I just want to introduce Altair Compose Actavite member release of 2019 version, latest version release. With that, we have new offerings with basic and professional editions. So you'll be having a free version of Compose Actavite and Embed for everyone. So professional version will be a part of HyperWorks units, and basic version will be accessible to anyone within the organization. And there's no restriction with the usage of number of licenses. And then we have open matrix for Compose, and another new licensing option we have with solid thinking units. So if you look at the basic and the professional edition of Compose, so if you look at the capability wise between the basic and the professional edition, so you'll have the IDE for debugging your script with respect to like TCL scripting, Python, and OML, and with all the toolbox like signal processing, control system, and optimization toolbox will be part of it, and you can lead your legacy data from your MATLAB and Octave. So the professional version will be with your CAE readers, HyperWorks integrations, and then special toolboxes and technical support. That will be a part of your professional edition. So this is the chart, and you have a link to download it, a free version within your organization. Like the website you have to go is www.altair.com/mbd2019. So with this link, you will be able to access our tools like Compose, Activate, Embed. These are our new tools for model-based design with the new capability of 2019 edition. Okay, so you can download it for free, and same as with Activate as well. So you'll have a professional and basic edition. Okay, so let me give an introduction to Activate. So Activate is a block diagram environment for modeling, simulating, and do optimization of a multi-body system. So how does Activate fit into CAE? So basically a 1D system simulation and optimization. If you take a physical plant model, it has different domains in it, like talk about pneumatics, kinematics, hydraulics, thermal, mechanical, and magnetics. These are the different domain, physics domain. It's a physics model. And we talk about control systems as well. So how are you going to control your physics model? So control systems, you have a feedback from an actuator or from a sensor. From a sensor, you take a feedback. From there, you build a control strategy, and it goes to the actuator. From actuator, it goes to the plant model. So this is how the entire flow of control systems comes into picture. And where the plant model may be your hydraulic model, maybe an electrical model, a thermal, depend upon your domain applications with respect to different domains like aerospace, automotive, any industry, you can use a plant model. So MotionSolve used for building a plant model, and Activate will be for your model-based design of a block-based approach for building your controls for verifying virtually. So if you do, how does Activate fit into CAE? As I say, like you have a co-simulation concept, like a mechanism of plant plus electronic software with the controller. The combination goes as a mechatronics. We are in the mechatronics world. We talk about IoT as well. So we used various ways of designing analysis in the model-based design. So basically, to design your control systems, we use model-based design tool like Activate, which can build your PID controllers. Basically, on the control side, you can talk about transient, Bode plot, Nyquist, all the control strategy, building up a state space equations. You can build your entire control model with respect to your plant. You can do a virtual both plant and control model as well, and you can do a co-simulation. That's a unique offering what we are talking about today. Altair offering has a seamless bridge between 3D and 1D. We'll talk about in the coming slide. So if you look at 1D system modeling, so I would like to differentiate you how 1D and 3D system behaves. Like if you look at 1D simulation model is useful for basically it's a mathematical abstraction of your real system. So if you look at a 3D CAE, a typical mechanical engineer, you look at shape and structure for modeling, but you'll not be looking into your function into it. So if you look at 1D models, rather looking into structural and shape, you'll be looking more into a function and visible of it. So how you can represent a physical model into a realistic math functions, you try to derive it and do it. So this is how I've taken difference between a 3D view and the 1D view. So if I look at 3D shape, you can just look at shape and structure or visibles, not functions. If you look at system modeling, you'll purely look into functions and visible. Functions are visible, not the shape and structure. So it go from analysis goal to level of detailed simulation and optimization level you go. So as Activate, I say it's basically a block diagram environment for model-based development, where you have an approach of doing, you can model and simulate a dynamic system, entire system. You can build a plant and control model. You can do purely a signal-based modeling, or you can do physical-based modeling, or you can do the combination of that. So physical-based modeling is how the physical component represent the real world. You like a resistor, inductor, or a spring mass damper system, or a gear. Like all these components are physically available. You need to drag and drop and connect, and you can model it. And if you want to build a controls with respect to feedback, you can do signal-based modeling. So that's what I want to talk about, signal-based and physical-based over here, as well as a mixed simulation is possible. So our simulation platform for parametrically, you can graphically model it, optimize it for both your continuous and discrete dynamic systems and their controls. So this is a simple example how the user interface of our Activate look. So here is a physical-based model which has a force, mass, and the damper. It's a physical model. And now you're going to control a physical model. You have a feedback system with as a PID controller. We talk about controls with respect to your reference input. So what are the error signal it tries to fit in your with respect to your PID values? And then after that, you're going to do an optimization as well, optimizing your optimal value of PID. So here, this is how you run the simulation over here, and you look at the response. How you can optimize these results, your transients and steady state. How do you fine tune your error? How you can optimize with respect to your reference signal. There's an example of mixed signal, physical and signal together with an optimization. So Activate key features, what are things you can model on a math model is you can model and simulate your continuous and discrete block sets. Dynamic systems can be modeled, and you can do mixed approach. As I've spoke about, you can do signal based and physical based modeling. It may be any domain you can model it if you know the math equations. We have all the block sets library available to build plant and control model, and you can do optimization of your controls, and you can take your legacy models from Simulink. We have an option to import your legacy models into Activate. So then the next key features is the seamless integration of different domains like MotionSolve with Activate, Flux with Activate, as that's a main new Altair offerings in the market, like where we have a coupling of 3D with 1D. Physics solver can talk to a math solver. So what is the importance of that? We'll talk up in the coming slide. So introduction to MotionSolve.
Yeah, so good morning all. So while introducing MotionSolve, probably I'll help you out to understand what exactly we do in terms of co-simulation application and what kind of applications we can simulate in MotionSolve. Yeah, so MotionSolve is a dynamic solver which has a comprehensive solutions to analyze, optimize the mechanical system and its performance. So what we do in a motion view, we build the multibody dynamics model, which you see the first picture of a robot which is assembled in a MotionSolve and which has a control. And then we are doing a co-simulation and we are solving it in MotionSolve. So which you see the second animation, which is solve, which is the numerical solver is a MotionSolve. And once we solve it, we do a further post-processing and evaluate the results in HyperView, HyperGraph. And if we have a need of further optimizing the results, we can go further to the next level and improve the results using HyperStudy, which is HyperStudy and optimization. And we are also having a MotionSolve DSA optimization available very soon. So this overall flow of doing multi-body simulation, and when we want to do a co-simulation application, we generally model the plants. So that is the plant inputs and plant outputs. So whatever the communication happens between the two solvers, it happens with the MotionSolve plant models, which goes into the another code or the 1D code, which is in this case an Activate, and which tries to communicate between two and perform the simulation. So what you can do with MotionSolve? So these are types of analysis or types of verticals. You can say we can do kinematics, we can do dynamics. So what is mean by kinematics is basically the study of motions, which can be a forward kinematics, inward kinematics, we can do over there, where the effect of motion is an interest to study. When we say the dynamics analysis, what we mean here is the effect of mass inertia and the forces would like to have a major contribution and would like to analyze them. We study that in the dynamics. Quasi-static and static is static and quasi-static are the slowly moving systems which we can simulate in a motion view MotionSolve. If you want to study the durability of your structures or the components, we can consider the flexible bodies. As the example, you can see it's a 4-poster car with a flexible body. Then we can do a low frequency level analysis as well, low frequency NVH. So the example shows it's a brake squeal application. We can simulate that using motion view MotionSolve. And we do multi-physics applications as well, whereas we can use controllers, we can use tires, we can use the hydraulic systems, we can use the drivers, we can use different tires. So these all complex physics can be clubbed together and solved using motion view MotionSolve and communicate with between other 1D codes as well. So that's about MotionSolve.
Yeah. So now we'll go into the co-simulation. So co-simulation definition, co-simulation is basically a process in which two or more solvers simulate simultaneously while exchanging the data between them in a real time to analyze the complex phenomena, which involves multi-physics such as structural, fluid, controls, and electromagnetics. So co-simulation needs. So if you look at today's products are multidisciplinary, smart, and connected. So if you look at the physical components, we spoke about like example like mechanical, mechatronics, or electronics. It has for different domains for aerospace, automotive, or heavy engineering, a plan model, a physical component. And then you have a smart components. That's how the control systems comes into picture. We talk about sensors, microprocessors, data storage, and then embedded and IO interfaces. So we are in the world of IoT. How are you going to connect these two products? As we say, we are system connected, car-to-car communication. We talk about all are interconnected. So if you look at the connective side, connected components like ports, antennas, protocols, networks, and the communication between that. And we have a cloud solutions. So these are the today's products, which has multidisciplinary, multi-domain, controlled, and then connected. So Altair offering on these multidisciplinary solutions, if you look at the slide, we are pretty much strong on the structural side. Everyone knows about our main DNA lies with the structural meshings. Like you read about HyperMesh, CAE driven tool, like on both on crash, durability, safety, we are pretty much strong on crash as well on the left hand side. Other offerings which can talk to our solver is coupling with multi-body with 1D simulation, a MotionSolve with a math simulation, math and system simulation. That's what we talk about, Compose Actavite and Embed. And if you look on the extreme side, on the right hand side, we have a low frequency and high frequency tool, which has electromagnetic simulation tools for EMI, EMC, and as well as low frequency for designing your motors, sensors, actuators, transformer design, starting from energy generation to conversion. And it has a coupling with OptiStruct for vibroacoustic analysis with different physics. Let it be magnetics, thermal, or purely electrical, we can do with low frequency tool. So we have the complete unique offering with our HyperWorks Altair suite of solutions, starting from structural, fluid, thermal, multi-body, interfacing with 1D, and then low frequency and high frequency. This is what we say is a seamless integration between our solvers. So today the more focus is on MotionSolve with Activate. And then this is how other Altair offerings on other domains as well. So this slides, if you look at this today's models, like I've taken 3 examples. If you look at today's suspension model, suspension, electrical motor, and electronics, I've taken 3 verticals. So we are calling models like 0D, 1D, and 3D. If you look at 0D, it's basically a first principle mathematical equation, a state space equation. A suspension, quarter car or half-car suspension model can be designed in 2 forms. A quarter car ride model, you can do with both open loop and closed loop, in the sense like active suspension as well as passive suspension. So you can do that in 1D form by doing your signal-based modeling. You can do the entire model in a signal-based by giving inputs like what is a bump square. You are giving a different road profile as an input and trying to model it and see the suspension stroke, spring mass, velocity, and sprung mass acceleration can be seen in the 1D form with respect to time. Same quarter car suspension model can be designed in physical-based model. Just drag and drop the component with the damper, mass, and you connect it a sensor and try to see the response. So this is a 1D approach you can do with purely in Activate. And if you want to do a co-simulation, then there is a 3D approach which you can do with MotionSolve. Here is the model. You can just look at the suspension. You can look at you can model this in the 3D view. And later you can do for the closed loop active suspension, you can take an actuator feedback and you can build the controls. So to build the controls, you can't do that with MotionSolve. It's basically a multi-body tool. So you have to rely on some control system software. So Altair has a control system software called Activate, which can do block-based approach to build your controls. Anything with respect to feedback, you can do that. So you can have an option of individually doing in 1D. 0D is basically you can do scripting, as I spoke about initial slide. Compose, which basically numerical scripting can be done in Python, OML, and TCL/TK. So we have a seamless flow between 3D, 1D, 3D, and 0D. Like we have a seamless integration. So 3D with 1D is the main option what we are doing in this today's presentation. Similarly, we have with electrical motor and electronics. So as I say, system integration platform. So with Activate, you can build controls. You can build Modelica for doing physical-based modeling. Activate as connectivity. Activate is an FMI complaint, which you can do co-simulation or model exchange. So within our solver, we have a multi-body dynamics. You can do co-simulation 3D with 1D, same as with electromagnetics. If you want to integrate with any third-party solvers, you can have a seamless integration with through an FMI connection. Through an FMI connection, you can talk to other third parties. So need for co-simulation. There are many simulation tools specialized for different domains like electrical, electronic components, mechanical and multi-body components, or hydraulics or CFD. So simulations are quite complex, composed of models of different disciplines, can be quite difficult in a single tool. That's what you need different domains to be like integrated together or do co-simulation. So model cannot always be imported or exported since they need to be appropriately solved on the same platform, same environment, or same PC. The tool coupling we call via co-simulation seems to be a general choice. Okay, so now how you can do co-simulation between MotionSolve and Activate. So MotionSolve with Activate co-simulation, you can the master and slave you talk about. So master may be an Activate co-simulation interface. That's the interface we give a bridge in to take your plan model into Activate and build the controls. So we have a co-simulation block available in Activate. which is a part of it. So slave will be your MotionSolve. So process 1 and process 2. So master is a slave algorithm, activate is a master, and MotionSolve is a slave, where master controls the process and calls the slave. MotionSolve and activate model must be modified for the co-simulation. So you have to know what is the output of your MotionSolve, which should be given input to your activate. What is an output of an activate which goes to the input of your MotionSolve model. So whether if you take an example of a motor, so input is an electrical input, and you find the output like speed, torque. How are you going to control this? You want to control the speed or a torque? That is the output which you're going to take a feedback and you're going to control. To do the speed or torque control, you need some controlling tool. So as an example, I'm saying, so you can do the coupling with this perception. So MotionSolve with activate co-simulation, like a planned input and output are accessible. Input and output exchange happens only at a specific time instant. You have to specify the solver time. So iteration is possible. So if you look at the Gauss-Seidel iteration is possible, like MotionSolve can interpolate after activate finish at step 1. So you can look at the MotionSolve, how it takes with respect to time domain, Tn and Tn plus 1 and Tn plus 2. So how the activate sequence of time domain, you can work with the co-simulation side. So here the MotionSolve setup you can do, I can just show, I can walk through one case study of unmanned aerial vehicles. So MotionSolve solver are used to define the planned inputs and outputs by leveraging the solver variables. So as I told, so you have activation and control has been done with activate, and MotionSolve you do the entire planned model. So the planned output which goes to the controlled input, and the control output which goes to the planned input to your MotionSolve. So co-simulation applications and examples. So I've taken an anchor case study, thermal study of a brake and braking distance. So we have taken the co-simulation taken to the line pressure and then wheel angular velocity. So we have a model coupled with activate. So the objective of this is to determine the thermal influence on the braking disc and the braking pad, the braking distance of the vehicle in order to optimize the system behavior. So solution, the entire system simulation using activate, like multi-body of a vehicle with the friction and thermal dependent models. You can represent the thermal model in terms of 1D as well as signal based model as well. And you can integrate 3D with axial with 1D coupling is as well as possible. So benefits, more accurate results, simulation runs faster and allows more what if analysis. So you can do what if scenarios. So running a math solver is always a fast compared to a structural physics solver. So both has its own advantage of coupling and getting out your benefits. This one case study, we have a lot of case studies. I've just showcased this for minimizing thermal influence on the braking distance side. So here is another example which I want to talk about is inverted pendulum example, a swing up pendulum, which is done coupled with activate and MotionSolve. So co-simulation. So this is the entire planned model of inverter pendulum. So you will see how to couple a 3D motion mechanism to control the system in activate. How are you going to control this 3D mechanism? So with respect to different 3D views. So this example shows a swing up pendulum control force coming from activate in the co-simulation side. How do you achieve this? So here you have the MotionSolve, which takes, this is a coupling block which is available to integrate with activate. So there's a co-simulation block available. So you have a system states, different states of control. The entire controller has been designed to control the force of your inverted pendulum. So controller, as we have created that as a super block, you can go inside the super block. Like a sub-circuit, the entire equation you made as a sub-circuit. Yeah, this is a vector system state including the pendulum angular and angular velocity and the cart position, how you're going to control on a particular angle. You want to control at 90 degree or 45 degree, how you're going to control. So the entire models, these equations have been modeled in activate based on the condition, how you're going to control your force. That control force has been given to the MotionSolve. So if else condition, these are the block sets available based on the condition, which gives you an input and drives your MotionSolve model, a 3D model. So in MotionSolve, you have a setup, the XML or MDL file is an input file as a MotionSolve file, a 3D file, where you can launch MotionSolve. Look at motion view, where the model which is done. It has bodies, a ground body, a pendulum, and a cart. So and you can look at the joints, different joints. And then the forces. There's a force acting on it. Now we're setting up the variables. Force. You have a solver variable also created for measuring the MotionSolve model, pendulums, right? So you're setting up the expression here, type an expression. So this will be the input to your Activate, the solver variables, the planned output of MotionSolve. So here you are, the output file of the MotionSolve is an MRF file, which has been put into the coupling block. Then this is the coupling block which specifies your number of inputs and outputs which has to be controlled. So that has been specified here, and then you build the controls. This is the model which you are running up is in the Activate. So you're trying to see the pendulum angle, angular velocity, cart position, and applied force in a 1D form. How it goes to 0 position with the disturbance, cart position is uncontrolled. Now you can look at the results in the hyper view. So these videos are available in website www.solidthinking.com. Like if you go to learn.solidthinking.com, you can look at all our videos, all the code simulation videos and example available. And as well as the solver files are there. You can download the tutorials and the video files. This is a solver input. So another example which I want to talk about is two-wheeler Segway scooter. This has been done with our solvers. So the entire plan model is done with MotionSolve, the multi-power dynamics. And then to design, to design the motor, we have used Flux for designing the motor based on the speed torque characteristics. What is the speed and torque you require to drive? We have done that with the physics solver, a finite element based solver. We've done the motor design. Once the motor design is done, then you need a coupling between your MotionSolve with Activate to balance the vehicle. How are we going to balance the vehicle? That is done with Activate. That's what you have a system. You do the entire system simulation with the mechanical system design, electrical system design, plus control system design. When you do the entire system simulation, and then you see the control with respect to closed loop. And then later we have to employ this onto the hardware targets. We have a tool called Embed. You can deploy your controls onto the hardware targets. So this is for the styling part. We have done with Evolve. Rendering is done with Evolve tool. So we use all our solvers to build this virtual two-wheeler Segway scooter, a self-balancing two-wheeler scooter. So another example, motor design using co-simulation. So in this, we used MotionSolve coupled with Activate, and then we have done with OptiStruct as well. So motor design is taken care in Activate. So if you look at this example, the problem is designing a motor for a given task. So pick up and move the flexible metal sheet from an object A to B. So it has 3 joints and there is a 3 motors, J1, J2 and J3 that we use with the Modelica, a physical based motor design. And MotionSolve and MotionView, we basically model rigid and flexible robot system. And we couple this and do co-simulation with Activate. And then OptiStruct is used to find the CMSM flexible body of a metal sheet. So here a rigid body analysis, we do solution. So build and validate a rigid system, a simple motor representation, a metal plate model for a rigid body. So here you can find the sheet metal stress and strain is done with our like pre and post tool like HyperMesh and OptiStruct. And you can find the stress and strain, and from there you pick up an object and then move. How are you going to control that arm forces that is taken care in Activate? How are you going to move the arm angle, that different arm joints has been taken care in Activate? How do you control the speed and torque? You can represent the different angle in degree based on the different arms. So that is done by Activate with MotionSolve core simulation. So here you can just see the 3D results compared. You can just see the similar in 1D results as well. How the moves and the joints moves up. So control. So the key takeaways of this core simulation is connect with Modelica subsystem to MotionSolve. Simulate the entire system in Activate. That's both with the plant and control model. How are you going to improve or design with system responses? You can fine tune that as well. So I'll walk you through an example of a quadrotor. So I'll load the, I'm just going to talk about the quadrotor. So if you go file, open up a model. I'm just loading a quadrotor model. So if we look at the quadrotor model, if you go to the body, so you have the ground body. You have there are 4 motors. The rotatory force has to convert into thrust force. So you have a left motor, which has a variable inertial properties are here. And you go to the right motors, a vehicle, the entire vehicle, a propellor left, propellor right, front motor, rear motor, the entire body of your quadrotor. You look at the forces, what are the thrust you're going to give? You have to convert your rotatory force to a translation force. So how are you going to control the speed? So first we'll model purely a planned model of a quadrotor and then try to run it. So you have a thrust left, right, front, and thrust rear and wind disturbance. Against the wind, how are we going to affect it? Okay, so let me run this file. So the analysis, what you're giving a start time and end time. Time interval is giving 0.01 second, and then end time is 5 seconds. You're doing basically a transient analysis simulation type. I've run the model. Let me animate this model. So here there is no controls toward the model. After me solving this quadrotor, so there is no control. So it is falling. There is no controls towards it. That's the need where you need the co-simulation between MotionSolve with Activate coupling. So now it's a purely a planned model. Now we'll do the co-simulation with Activate. So what are the importance you need for this? If you look at the quadrotor model, quadrotor control using co-simulation between MotionSolve and Activate. So the quadrotor have become a popular recently in unmanned aerial vehicles. So there's a 2 set of controllers which has how you're going to control your altitude, pitch, and then the roll. The control of a vehicle motion is achieved by alternating the rotatory rate of one or more rotor disc by changing its torque, load, and thrust or lift characteristics. So this is the main controls we're going to do with Activate. So the control of quadrotor path against the wind disturbance. The quadrotor is modeled in motion view and simulated in MotionSolve. That's what I showed you, the plan model, which doesn't have a control. So we need to model a control. So the model includes the wind disturbance. Activate simulates through the co-simulation with MotionSolve will implement a controller to impose altitude, path, and then wind effects. How are you going to control on a particular height? So for that, how are you going to use the PID controllers? So fixing up the proportional value, integral value, and derivative value, how are you going to stabilize your particular altitude path and the roll? How do you control the motor control? That is taken care, they activate. So the entire quadrotor model, which I've shown, which has 2 rods and propellers and 8 joints and 5 forces are acting up, which I showed the front rotation, how it has to rotate. It was rotate in a clockwise or anti-clockwise direction, which you have the controls toward it. That control signal is being given from activate. So this is the motions, which has different throttle command and roll command for both left rotation, right rotation, front rotation, and then the rear rotation. So how are you going to control your thrust against the wind disturbance forces? So the force thrust values are given. And then this is the control model we done with activate. So if you look at activate model, there is a coupling component available to load your MotionSolve model, and then you take a feedback. In the feedback, you're trying to put a PID controllers. One is to target the path like X and Y altitude control, and then pitch control, and then the roll control. These 3 controls we use the PID controllers. So control system has it has a difference. So PID controllers can be set up with the experience, like you can do trial and error method. You should know the controls knowledge on how the system behaves, like you should know the board plot, Nyquist plot, how the system response behaves. And based on the experience, based on the response, you can try to fix up your PID values. And if you know the formula, you can put an actual value. So as a domain engineer, you have to know what exactly we're going to control. So control system blocks are there, but we have to put accurately control based on the different domain applications. So in this case, we are trying to do 3 controls. One is pitch, altitude, and roll. So MotionSolve model is over here. That's why we have a coupling model called MS plant. These are the targets we're going to control, path and altitude targets. And then these are the plots we're going to visualize in 1D as well as in 3D. At the end, you can have a comparison between 1D and 3D results. And this is a controller we have built. The controller blocks has been built in Activate, these control components. So this is the altitude in 1D results. You'll find the roll, pitch, and path. So now apart from this, it's not only we have done the MotionSolve coupled with the Activate, but we have done the entire design and implemented in our, during our ATC, we have shown the physical drone flying up. So the structural part is taken care with the Altair Inspire Motion. And then we have done the FEM analysis and the weight optimization is done. And then later we have done with MotionSolve and Activate coupling to do the entire system simulation to virtually validate it. After we virtually validate how the drone, a virtual drone, going to behave, then we done the realization of this onto the physical prototype. And we used Embed for driving the motor and controlling the motor. Everything has been taken care on the microcontroller side with respect to TI microcontrollers. So now I'll run the Activate model. So this is a model. If you look at this is the user interface of the tool. So if you look at the palettes, we have all the block sets available in Activate, like signal generator, signal viewer, signal importer, dynamic models, math expressions. So these are the built-in blocks available. If you look at the co-simulation block, there's a block we have a block to interface, like these are co-simulation blocks. It's available to do the co-simulation with MotionSolve, Flux, and with an FMI complaint. So here is the MotionSolve model, MS plan model, which has the MDL file, solver input file, and then the solver output file is over here. And then there's these are the control inputs and control plant outputs. So plant output, which comes from the MotionSolve, and the control input, it comes from the Activate. So and then you can just specify the solver time over here. What type of solvers you want to choose? What should be a start time, end time, and time step can be specified here. And the solver parameter, solver type can be specified here as well. We have different type of solvers like continuous and discrete solvers, and you can just specify the tolerance and given the time step as auto. Okay, let me run the simulation. And then you should set up how to set up these PID values. Look at how you set up your professional gain, integral gain, and derivative gain Towards this, if you want to look at this model, you can go the enter into the model. So you have the ready-made PID blocks available here. Here are the PID controllers. You can build your own PID, or you can feed the PID parameters as well, and you can go inside the sub-circuit block as well. Okay, the entire PID values this is for your controls of your altitude, X and Y, and then this is for the roll and pitch control. There is a gain block over here. Okay, let me run this model. Yeah. So I'm just solving this file. Then I can just show the animation with respect to 3D, how it is controlled. So you can just see the run real-time results. You can just see the plots with respect to time. Oh, sorry. Oh. So you can just see the different plots here. Okay, it's done. So now let us see the results in the motion view. So I will load the solver file. So I'm just opening the HDD file, the solver output file, which I have run right now. I'm just loading the file. Just a sec. So now, the previous model which I've showed, this is a model which I want to run this and show this a uncontrolled model, which I'll show the control model now. Animate the results. Okay, so there is no controls now. I'll run this without control. I've previously shown. See, there is no controls. Now let me run the control model now. The solver output file which we ran the output, I'm just adding the S3D file. Apply. Yes. So now you can look at the control model with respect to particular type. Just load the solver file. We load the file. Let me run the file. That file is in just a sec. Just want to add the output file and then show you the control model. So I just want to compare the result and show you with controlled and uncontrolled. So that's what I'm putting the solver file. So it's overwritten. That's the reason again I'm running it back. Yeah. Just a sec, that should load. Going stuck. It's stuck actually. Yeah, now you can look at the control model. Now you can find the altitude and pitch control. So this control signal has been driven. The control model which we done with co-simulation with Activate is the model which I am loading it. Previously, there's no controls. After you modeling it, it's flying up on the particular altitude, height, and pitch. So it has to rotate the propeller against the wind. You can do this with respect, like you can do our CFD as well against the wind. So it has different domains. So this is a pure example of multi-body with Activate co-simulation. And then you can do the structural design. We have done that. We have a paper also. We can just share the paper. We'll share our mail ID. We can just share you this use case, which has been physically modeled as well. Okay. So now we'll go to the summary. So Altair Activate is an environment to build and simulate both 0D and 1D systems, complete system simulation. So Altair MotionSolve provides an environment to build, simulate, and improve your mechanical system. So the most mechanisms today are controlled by computers since they need for co-simulation. So Activate provides an effective platform for co-simulation with MotionSolve. Flux and other FMI compatibility codes to simulate a real-world problem in all the complexity. So Altair is a one-stop solution where within our HyperWorks units, you can build your multi-body, you can build your controls, structural optimization. You want to do optimization of a structural, you can do with Opti. We have as well as with CFD, thermal and fluid. We have various options to seamlessly drive between 0D, 1D, and 3D. Okay. So these are our mail IDs. You can just make a note of it, and we can just share the case study, and we can look into your problem. And we have a lot of case studies. Jitesh take care on the MBD side, and I take care on the controls. I can give a detailed presentation later individually as well. So again, I just want to touch upon the 2019 release, the basic and the professional edition of Compose, Activate, and Embed. So the release here, like Altair Compose, Activate, Embed as basic and professional edition. And we have a new licensing with solid thinking units as well. Solid thinking units is completely or Compose, Activate, Embed as a bundle. So here is the basic and the professional edition chart. What is available in basic and what is available in the professional, which is part of HyperWorks units. And you can download it www.altair.com/mbd2019. So here you can download the free version. So there's a link. Okay, same as with the Activate. So Jitesh and now question and answer. Any questions? Check the chat window.
Yeah, you can type a question in the chat window.
So with that, we end our presentation, and we look forward to an interaction with you all. So if anyone in the audience looking at this presentation, hearing this, and if you have any questions, please put forth in the chat window. We can have a discussion right now. Of course, you can also write to us on email and let us know if you have any further questions related to this topic.
Here is the mail ID. So you can contact us jitesh.porval@altair.com and chandrakumar.manovalan@altair.com. So you can just drop us a mail and we can have a session. Yeah. Yeah.
Yeah. So there is a question from Pradeep.
The question is that can we use Activate in the existing token? Yes, Activate takes 15 HyperWorks units, so you can use Activate. Pradeep, you can use Activate. So with the same existing HyperWorks units, you can use.
Not just that, but you also have Activate the basic version. You don't need HyperWorks for using Activate Basic. It's available as a free download for anybody who wants to use it, even outside of HyperWorks.
Hemant also wanted the email IDs of Chandra and Gitesh. So I will share those email IDs. Of course, it's there on the screen as well, Hemant. You can write to Gitesh as well as Chandra Kumar. Just go down. Just go down. Yeah. I think that's it. So yeah, there are no further questions on the chat window. If you have any further questions, do write now, or else you can even email it to us. So that's fine. Okay, there's no further questions. So I hope the session was informative and it basically addressed some of the new concepts related to co-simulation and how you can couple Activate with multi-body dynamics. Of course, tomorrow we have the third session, which is basically, or day after, sorry, on Friday, the 2nd of November, wherein we'll be showcasing some of the case studies related to co-simulation with the Altair Flux and how you can manage those type of couplings. So with that, we end the presentation for today. Do write to us and let us know if you have any further questions. We'll interact with you. Thanks once again to everyone who have attended this session. Have a good day.
Thank you all.
Thank you.
Yeah.